like to acknowledge the Gadigal people and the Eora Nation on whose lands we are actually standing today. And I only found out really 2 days ago that there were really sea people. So, you know, they live off the sea, and the women were actually much better than, you know, at fishing than men, which, you know, I used to put the, you know, fishing line from the shore, and the women would actually go out with canoes, with babies, they had to feed at the same time with their, you know, cooking pots and everything, and then, you know, all the skill with the fishing that goes with it. So anyway, just a little admission from what we were going to talk tonight. But yeah, they were the first people here.
Okay. Thanks, Katerina. Okay, before we start, look, we'll have some housekeeping announcements from the ASEG and SMEDG, and then we'll have the presentation of the AIG Distinguished Service Award to Wendy Corbett. That'll be followed by Steve Collins presenting on some geophysics. So with our housekeeping, we'll start with the ASEG. Let's get my thing over there, in the way. Oh, sorry, I had to, excuse me for that. Okay, so let's go back. Firstly, thank you to Fender Geophysics for sponsoring tonight's talk. They've been the development of the Heterodyne method. Am I going the right way? Okay, thank you to the corporate members of the ASEG, branch sponsors. Okay, yeah. With any questions and answers, we'll set up the chat thing. We'll get to them later. Okay, member benefits for ASEG. Keep in touch. Okay, that's it. And look, just a few events coming up for SMEDG. In about 3 weeks, we've got the gala, the 50th anniversary gala conference and dinner. Registrations for that close on the 17th of August, and the event's on the 25th of August. We have more meetings come. September, October meetings are now taken, and October, November meetings, full suite of meetings, and also the end of year cruise. So on that note, can I please hand over to who's do the presentation to Wendy. Should be a video on that, yeah. Is the video working? It will be, yeah.
So, hello everyone. My name is Katerina. I'm the chair of the AIG, and tonight we've got a special night. In addition to tonight's presentation, we would like to give Wendy her service award. I will only tell you very, very briefly about my interactions with Wendy, and then Doug, and then Chris, who is the chair, who is the president of the AIG, who actually came from Brisbane only specifically for this award tonight. I actually became a chair because Wendy said, "Can you please help me for 2 months?"
I'll just turn off screen share. I think we're not getting through.
And yeah, and then Wendy left, and I had to stay and do all of this work. So, but it's been a good 6 or 7 years now, and we've done a lot of events with students. We had core logging, which everyone was so happy about. Victoria has asked us to hold an event in Bendigo, I think, was it, for them. And we had a mentoring program which didn't really take off that well, but you know, there were some people who benefited. And we also do a lot of student events here in New South Wales. So every year we go to universities. We now cover 3 universities. We talk to them from different perspectives. So, you know, depending on who we can get, so usually exploration geology or mine geology or hydrogeology or environmental, you know, aspects of the environment. So yeah, so we just try to promote the profession, and that's what we've been doing for the last 6 or 7 years. But can I please, Doug, would you please be able to come up here and talk a bit about the award and Wendy, everything this really special award tonight.
Pleasure. Yeah, look, I feel very fortunate to talk about Wendy as well. Like Katarina, Wendy trapped me into 7 years ago into being part of the Mines and Wines Committee, which I thoroughly enjoyed, and she mentored me very much into the role. I feel very fortunate for that. She was a great leader of that conference over many years. Wendy, I'm not sure whether many of you know or not, but Wendy was a pioneer female geologist back in the Northern Territory many years ago. Was involved in the discovery of the Ranger uranium mine, where she lived for many years. She went on to start a number, or be involved in the listing of a number of junior exploration companies here in New South Wales, Plat Search, Veriscan, I'm probably saying that name incorrectly, Wendy, that's right, okay. Eastern Iron, Thompson Resources, and Silver City, and which she worked for many years. And there are many young female geos, particularly, that benefited from Wendy's mentoring and expertise over the years, and I know a number of them, and as a young geologist, I also benefited from that. Wendy's involved, as I said, with the Mines and Wines from 2007 through to 2015, and she did a great job kicking that conference off and got it to the position that it is at the moment, and really promoted the Mines and Wines really well. A number of other conferences that she was involved with from SMEDG and AIG's perspective as well. So she's made a hell of a contribution to our industry over that time. And so I'd now like to hand over to Chris, who can come and speak about the award.
Thanks, Doug. So my name's Chris Dickinson. I'm the president of the AIG at the moment. I expect nobody will have recognised me because I haven't worked in exploration since 1994. I'm from north of the border. So I'm actually a hydrogeologist by trade. So I think Katarina might be the only one that's crossed paths with me in the professional circuit. I guess, first of all, I just want to acknowledge the AIG's awards committee. They did a fantastic job in developing this award, and also in identifying 6 fantastic candidates. So we have candidates in WA, South Australia, Queensland, Victoria, Tassie, and of course, New South Wales. When this concept of a Distinguished Service Award was raised, as a board, we were very enthusiastic about supporting it. The value and the importance of volunteerism it cannot be understated. So this is an award which recognises outstanding commitment and volunteerism, which has pushed forth the geoscience profession. In this particular case, I guess I've been involved in not-for-profits for around 10 years now. And to me, volunteers, and particularly volunteers who put such significant effort in, are the lifeblood of the organisations. They provide the drive and the passion. They provide the continuity. They provide the consistency that's needed to deliver members' services. We just simply wouldn't be able to survive without them. I only met Wendy for the first time this evening. Certainly, I've had a close look at the nomination process, and I think she's a wonderful candidate. So on behalf of the AIG board, the members, on behalf of the AIG, I'll just mention the awards committee of Mike Smith, Leah Moore, and Jeff Turner. They were the key to all this. On behalf of the committee and on behalf of the New South Wales branch of the AIG, I'm delighted to award the 2022 Distinguished Services Award to Wendy Corbett.
Thank you. Thank you very much. Am I allowed to say something? Please. Just quickly want to say thank you. This is a really unexpected privilege and honour. Thank you. I'm just blown away. But I don't feel I deserve it. I think that really I'm only as good as the committee I worked in. And there were some wonderful people in that committee. There was Ian Noyce, Peter Lewis, Mike Smith, Greg Corbett, Katarina came in. Sam Lees. They're all fantastic, talented, hard-working volunteers. And I feel as though I'm accepting this on behalf of all of them, so thank you.
Screen working again, excuse me for a minute. Just okay, just give me a minute to. What's happening here? Sorry. No, I'm not. Sorry? Yeah. You got a cursor on the screen. Oh, okay. Ah, very good. Okay. Just see the black share screen. Where's no. I was working before. There we go. Okay, can we please, before I welcome Steve, how many are likely to be coming for dinner upstairs? Can I have some hands so I can let them know, please? Okay, thank you. Upstairs? Or downstairs, sorry.
Mark, we're not seeing a shared screen.
I think we need to recalibrate.
Mark.
Sorry?
We're not seeing a shared screen.
Aren't you? Oh, no. Okay. Tick, let me go. Okay. Okay. Is that showing?
Brilliant.
Okay, thank you. Okay. Okay. So, I had Steve's bio. I'll put it out ready to welcome Steve, but I've left it at home. But everyone knows Steve, a long-standing member of ASEG, SMED, and a well-known geophysicist. So if we welcome Steve to the
Yeah, thanks, Mark. Having done SMED meetings for a long time, I know the difficulties with the technology and all the rest of it. So, except that I don't understand this, how am I going to get this on the screen? Come on, there's a picture of the Tumut River or something.
Hit the space bar.
Space bar, thank you. Enter. Okay, I do apologise to all those people out there in Zoom land. I hope you can see this. I'm going to have to turn around and watch the screen every time because it's not in front of me. Oh, there you go. Oh, no, no. Yeah, you might have to do that.
It's usually the arrow button or the mouse. Yeah, click on the mouse or the arrow button.
Thanks, Jim.
Oh, cool.
Oh, it's a black box.
There you go. Yeah, anything technologically completely defeats me, I'm afraid. Yes.
There you go. Got it.
Right. Okay. Righto. Can I use the scroll thing? Is it on there? Can I? Yep. Okay. Okay. Yeah. Sorry about the delay. And I hope this is going to take a while because there's an awful lot of explaining to do. So if anybody wants to get up and leave, I understand. Okay. Let's start. When I went to the Mines and Wines, I noticed that everybody had a disclaimer, so I thought I better put one up there. It's in legalese and in suitably small font, so you can't read it. But actually, there's something important on the bottom of this, which is at the bottom. And I want everybody that's here to take note of the fact that this is research. It's actually not about exploration. I know very little about the exploration that's currently going on at our field test site. And if anybody else asks me, how deep will it go? The answer is, I don't have a clue. And because we don't even know if it works yet. So whatever questions you ask, don't ask me how deep it goes because we don't know. We hope it works. It's pretty exciting. Okay, I'll give you some history. Here we are, a couple of decrepit old geophysicists sitting in at their retirement 7 years ago, doing what they've been doing for the last half century or so, which is having lunch at the pub, drinking red wine, and discussing various things, including our career as geophysicists out there using arcane tools to look for minerals and confuse geologists wherever possible. And Bob gets up and he says, hey, he said, I can't believe that I'm retiring and nobody's followed up the work that we did 40 years ago for my thesis. There have been a couple of papers and most of those have quoted my thesis. And when you read the papers, it's obvious that they haven't read it. And what the hell? So we're sitting there and so we've had a couple of glasses of red and he said, well, we're retired. We've got plenty of time. It's an interesting project. We've got reasonable resources. Let's give it a go. Why not? After all, how hard could it be? That was 7 years ago. So we went to a smedge or an ASEG, I'm not sure, whatever, meeting. And there we cornered Andrew Sloop. We knew we'd need some logistics help, wires and all that sort of stuff. So, and we were reasonably friendly with Andrew. So we thought we'll get to Andrew and ask him if he's interested. Well, as it turns out, he was fascinated by what we told him. And one of the things he said is, you better speak to Keith Leslie because Keith is the total guru on building electronic equipment for geophysics. He works at CSIRO. And we knew Keith a little bit. So we gathered Keith and told him what we wanted to do. And he went, yeah, that's fascinating. I'm in. So there we are with the four of us, and they're the four authors for tonight's talk. Okay, so what is it? Well, what are the properties of sulfide bodies that you want to go look for? They're heavy, seas, gravity, blah, blah. They might be magnetic, all those things. But the one thing that hasn't been investigated, the fact that sulfides are actually semiconductors. There's even textbooks about it. And if you go to Google and you type in a search on semiconductors sulfide ore, you get about 500,000 hits. 100 years ago, they knew this. When people 100 years ago wanted to listen to the radio, they used a crystal set. The active element of a crystal set, does that cursor come out on here? No, we don't get a cursor on the screen. Okay, the active element of a crystal set was what's written there as a detector. And that was using a device called a cat's whisker. A cat's whisker was a wire just touching on a crystal, hence the name crystal set. That crystal was galena. And the contact between the wire and the crystal of galena acted as a rectifier. It allowed electricity to pass in one direction and not in the other. Now, who would have known that you put your moggy together with a lump of galena and sparks would fly? But that's the way it is. Now, if you think about an ore body and a sulfide ore body, as far as the electrons are concerned, they're whipping along and there's absolutely no difference between the cat's whisker in the top of that slide and billions of junctions between various types of grains in the sulfide ore deposit. It's even more complex than that because the type of semiconductor that it is, including pyrite, but particularly galena and all the sulfides, depends on the impurities in those crystals. They might have P-type or N-type. And I'd like to thank Chris Wilkinson, who's sent papers on the semiconductors properties of pyrite. And pyrite can be a P-type semiconductor or an N-type, depending on whether there's antimony or whatever in the crystal structure. So there's no difference between the cat's whisker, the active element in a crystal set, and the junctions between grains in a massive sulfide deposit. So that's all very nice. Whoopee-doo, that's great. But how would you go about detecting that? And this is where Bob's thesis came in. He investigated 40 years, 50 years ago now, several ways of possibly detecting that. And the most promising one was to use the Heterodyne principle. Now, that's a strange word, and any electrical engineer will know instantly what it means. Every time you use the internet, you download, it comes over the NBN, the frequency changes from optic fibers, whatever, into something, and then it's downloaded to something that you can see. The process that does that is heterodyning. Every time you turn on an analog audio radio, that radio is known as a super heterodyne. This principle to electrical engineers is day to day. To geophysicists, not so. So what is it? Now, I've got to say that this gets a bit technical for a few minutes, and I see in the audience here a number of geologists, a large proportion of geologists. So bear with me and just think about this. As your eyes start to close, think about how the geophysicists feel in the audience when you're up the front talking about paragenesis or palinspastic reconstruction or phase diagrams or whatever. Bear with me. It won't take long and it won't hurt a bit. So imagine you put into the ground current, traveling AC current, traveling at whatever frequency. Say you go to your PowerPoint and you put that straight into the ground. And apart from fusing your house out, you get current in the ground that might be at 50 hertz, whatever, backwards and forwards and backwards and forwards. And imagine that is the top profile here. Now think about what happens if you add another frequency at a slightly different frequency. You add them together. So wherever these things coincide, you get a peak. And wherever they coincide in a negative sense, you get a zero. So they add together and they make this fairly complicated pattern down the bottom here. Now, what's really important to think about here is that there's nothing special happening here. That looks complicated, but it's just the two signals. They're just in there together. There's no mixing going on. There's no hanky-panky happening between these two signals. They're just walking along side by side. They're not even holding hands. Okay, so here we start with that signal. And if you think about it and look at it carefully, you'll see that the strength of that signal comes and goes. Now, everybody in exploration has flown around the world in light aircraft with twin engines, and you can hear when the engines aren't quite going at the same ears, whoa, 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 whoa. And that's the beating between the two engines. The frequency isn't quite the same, so you get this beating effect, which is you can see here. The thing about this is we still have just the two signals. That's all. There's no interaction between them. It produces this signal, but the red curve here exactly cancels out the blue curve. But what would happen if you put something in the ground that stopped the current going the other direction? Suddenly you wipe out the blue side and you're left with a resultant curve. The first two curves I showed were about 10 and 13 cycles across the screen. In this case, in the bottom here, we end up with a resultant that it was the difference between those, about 3 cycles. So we end up with, suddenly we have magically made a signal that is the difference in frequency between the two that we started with. It's not apparent in the top curve here. It's a result of the nonlinearity, the diodes or whatever you like to call them in the ground. That's what we're investigating. Okay, so what we're really looking at here is putting in two just sinusoidal signals. You put them into some sort of, it doesn't have to be a diode, any sort of nonlinear process, electrical process. When I say nonlinear, I mean nonlinear between voltage and current. So when you double the voltage, you don't double the current. It's not a nonlinearity in time like IP works on or something. It's an electronic effect. It's just the current isn't proportional to the voltage. What you get out of that is the two original signals on this map, F1 and F2, and at the top, the one I just demonstrated, which is the difference between them, F1 and F2. You also get frequencies equal to the sum of those two, and also integral multiples, like integer multiples of those two frequencies, like F1 plus 2F2 at the bottom, or 2F2 minus F1, and all those integer multiples of those frequencies. That whole zoo of frequencies suddenly appear because of the nonlinearity. We normally plot that as a spectrum, which is the strength of the signal as the y-axis versus the frequency. So when you consider our two sine waves wandering along hand in hand, we have at a certain frequency, a certain amplitude. There it is, F1, it's there. And we have F2, it's there. And down at the bottom, we have whatever noise there is in the environment. In reality, particularly with the system that we use, you also get harmonics. These are multiples of those frequencies. They're almost impossible to get rid of. If you buy hi-fi equipment or something, you'll find a parameter called total harmonic distortion, which should be very low because in hi-fi, you don't want these things appearing. But in our system, which is actually a mechanical system, they're there. They come out of the alternator. We can't help it. Just out of by a point here, anything in color at the top in the next couple of slides, anything that's written in color is what I'll refer to. Anything in brackets is what it is. Technically, if you want to look it up in Wikipedia, you can look up that term. So harmonics and the primary frequencies. Now, in reality, you go out in the field and you actually do this and you measure the currents. This is from our last field test in an area with no response. We see the spectrum here and we see our two frequencies that we're transmitting, in this case, 48 and 72 Hertz, really nice, clear responses. And we see the harmonics. We also see the fact that we were close to a power line. So we get a 50 Hertz signal and also a harmonic at the 50 Hertz. I should stress here that the noise level, this line here is actually, this is a logarithmic scale. So this line, the line at the top, oh, sorry, the cursor doesn't appear on this, but the line, dotted line at the top is 3 orders of magnitude above the solid line in the middle. The noise level is about an order of magnitude. So there's a factor of 10,000 between the noise level and the signal of the peaks. If you've got nonlinearity, you get what we call the mixing frequencies, which is the difference and sum frequencies. And you also get what we call higher order terms, intermodulation products, if you want to look it up. You get a whole zoo of frequencies. And in reality, what that looks like in the field is your original signals. And this also is a signal from our last, this is real data from our last survey, taken about 200 meters from the previous survey. What you find is we're further away from the power line, the 50 Hertz signal is gone, and we have the difference frequency, the sum frequency, and by coincidence only, we also happen to have one of these higher order effects coming in. So it's simple. You put in two sinusoidal currents. How easy is that? Into the ground, and you wander around and you look for the difference in some frequencies, and they're your sulphides. How easy is that? But why would you bother? You've already got IP, which is likely to work better. Why would you bother? And the reason is discrimination of minerals, because not all minerals are semiconductors in the same way, and specifically graphite, pure graphite is not, it's a conductor, not a semiconductor. Impure graphite is a little bit semiconducting, but our tests have indicated that it's not semiconducting enough to have an effect. In other words, the response we get from sulphides and from graphite are different. So let's have a go. You know, that's where we were sitting there in our red wine encouraged state in our retirement. Let's have a go. How hard could it be 7 years ago? Watch us pull a rabbit out of the hat. The trouble with things that are non-linear is you're never quite sure what you're going to get. And that's what we found. It's been an interesting road. We knew there were going to be some problems. We knew that we couldn't put both signals into the same point in the ground because the whole process depends on the density of current. And immediately around the electrodes, there's probably at least 1 million times higher current density than there is somewhere out at the middle of the survey. We also thought that these should be about the same. The two signals should be about the same. In fact, we've done some laboratory tests that show that that's probably not a major issue. So we started with what everybody's pretty familiar with here, which is the gradient array IP survey. And typically you put a transmitter that's transmitting over a whole area to create a nice uniform field in the middle. Now you've got a couple of guys out here taking measurements. They're kneeling in the mud. There are snakes and spiders and thistles. And they're out there diligently collecting the data. We modify this, modified in a couple of ways. One is by putting two transmitters out. We have to separate the two signals where they go into the ground. We can't have that high current density with the two signals through it. So we separate them. And the other thing we've done, given the age of our crew, is given the operator a seat to sit on to keep him out of the mud. He's got arthritic knees after all. And he's also got a wine cooler and a bottle of heart pills, just in case. We did some laboratory testing, and I'm not going to talk about that. Alan Ertel has already given several talks on the tests we've done, but I put it in there, this slide in there specifically because just to show you that there are 6 electrodes, even for our laboratory test. That's Mallee Bull MB, I think. That's a bit of Mallee Bull core there. We have 2 connections to the piece of rock for each frequency, plus 2 for the receiver, just like we do in the field. I'm not going to talk about that, but I will show you one spectrum out of the field test. This is actually the spectrum produced from a lump of Q River ore, sulphide ore, which is actually one of the same samples that Bob White used on his thesis half a century ago. Just happened to be sitting in his basement. Who would have known? And as you can see, we've got, you probably can't see all that, but there are harmonics and there are mixing frequencies all through it. Our interest was to see what actually happened in the field. Your laboratory tests are all very well, but Bob and I and Andrew particularly spent our life in the field, and we wanted to get out there and just give it a go. We looked at field sites, Mallee Bull, Girolambone, Mount Bulga, whatever, and we came up with Kempville, which is the perfect site. It's perfect for a number of reasons. It's polymetallic, it's semi-massive in places. It's mostly barite, but there are sulfide lenses in it. It's directly adjacent to Ordovician sediments, which have some black shales in them. There are hundreds of drill holes. It's been surveyed with every geophysical technique known to man, and several that aren't. The company Argent Minerals owns the property, and Argent have been fantastic, actually. I can't thank them enough for access to the property. Argent owns the property. It owns the exploration license and actually a mining lease over the deposit where we're surveying. So access is no problem at all. There's accommodation, which includes 2 farmhouses on site. They've bought the farms, so the farmhouses are there, and it's really quite good accommodation, so long as you don't mind sleeping with wombats. It's secluded. It's in a blind valley with a public road, all-weather road that goes nowhere, so there's no traffic on it. There are no fences because they've all been cleared out for the possible mining operations. It's just almost economic. It's close to Sydney. It's only 3.5 hours. If we've forgotten to bring one of the transmitters, we can whip back into town and pick it up. And the one thing that I didn't add to this is that it has something that I've never seen anywhere else. And I'm glad Katarina's here because she's the one that did it. It has a drill hole in the middle of our survey area that has groundwater coming out of it under pressure. It's been capped off and they have a tap on top of it. So if we need water to water our electrodes, what do? You get a bucket and you walk over to the drill hole, you turn the tap on, there's your water. It's geophysicists' paradise, I tell you, it's fantastic. There are some problems. It's a bit cold, particularly at this time of the year. It's halfway between the 2 towns that boast about being the coldest town in New South Wales, Oberon and Blaney. Kempfield is halfway between them at a slightly higher altitude. This was our first field test, and that's our second. Those white streaks you can see, that's sleet travelling horizontally. It's not a pleasant place to be in winter. And the second problem we discovered is that if you use a bunch of old farts who have spent their whole life doing surveys, they all think they know how it should be done. It's like herding cats. Okay, some geologists. Since we've got some geology here, we're going to talk about geology. And for people that aren't geologists, okay, so somewhere in the Silurian age, sitting on the floor of the ocean, there's a volcano. It's spewing out various material. At the bottom there, you've got the volcanics, that's tuffs and rhyolites, odd bits and pieces of sulphides, whatever, through it. Then you get a more quiescent period of the volcanism. You run into volcanoclastic rocks, maybe things tumbling off the side of the volcano, maybe odd spurts of volcanism, whatever. And at the same time, there are vents on the seafloor. You've got blacks, you've got smokers, you know, black smokers, pot smokers, white smokers, I don't know. They're all in there exhaling, and they're exhaling deeply, and they're spitting out mostly barite. The barite, which contains a lot of silver, is the main mineral, main economic mineral at Kempfield. But also in places, there are lenses of sulphides being formed. Above that, you've got sediments. This is only a couple of kilometres from the Copperhania fault zone, which is a crustal scale fault which travels through eastern New South Wales. So it gets compressed and it's thrust up against, it's deformed and thrust up against some Ordovician sediments which contain the black shales. Then it was late Silurian, it was intruded by granites and a whole bunch of cross faults. And then we have today the geology at Kempfield. Now the area with the red circle is the area that we're surveying in. So I'll just zoom in on that. We got granite, we got the Ordovician sediments, which include the black shales. You got the volcanics at the base of the sequence, and you come up through volcanoclastic sediments and these bits, masses of barite everywhere on this prospect, up into the sediments. Now, I really need to apologise to the geologists that have worked on this project. Vlad is somewhere in the audience here. Vlad, I'm sorry. And Todd McGilvray, if he happens to be sitting around, and all the other geologists. Oh, Dave Timms, of course. Dave, if you're up there somewhere looking down, I apologise. Does anybody know if they get Zoom in, Kevin? or only in the other place? Okay, Dave, I'm sorry, but the fact of the matter is that the only thing that counts to geophysicists is the black shale and the sulphides. We're trying to distinguish between one and the other, and that's what makes it a good site. So that was all on behalf of the geologists. I hope you appreciated my total stuff up of the geology of the area. So here we are, black shales and sulphides. 2017, 5 years ago, we set off with stars in our eyes. We were going to use modified IP transmitters. So we had 3 of them. And a cast of thousands, of course, with 3 IP transmitters. Enough cars to make it look like the parking lot at Myers on Boxing Day sales. And there we were. The Ordovician rocks are just slightly to the left of this image, and the sulphides are under the hill on the right-hand side. Here's our setup, all the transmitters. But wait, we need to find how are we going to map this? How are we going to make a map? There's no point in putting a bunch of spectra up on a map. You can't do that. We have to develop something that we can summarize the results. So we invent a new parameter by direct comparison with IP, chargeability. A new parameter will say we look at the 2 main mixing frequencies. Now we divide them by the primary frequency, and the reason for doing that is because variations in resistivity will cause a variation in the signal, but if we normalize it by dividing by something else, we take that factor out of it. Because the secondary signal is about at least 1,000 times less than the primary signal, we multiply by 1,000 so we get a reasonable number that comes up. And we call it mixability. And one of our crew has a heart attack. Where is he? He doesn't like the term, and I think he still refuses to use it. But I figure that when time domain IP was first invented, people said, we'll call it chargeability. And everybody went, what? That's a dopey name. But that's what we use now, you know? So we have a parameter which we call mixability, which is the main secondary frequencies divided by the primary frequency multiplied by 1,000. Just to confuse the issue, the units are millivolts per volt. Will this lead to confusion with IP? My guess is yes. And to all those people out there, I'm sorry. But that's what it is. It's millivolts per volt, just like IP is. It's an entirely different parameter. It's not the same as chargeability. So we have this thing called mixability. And I'm sorry, Keith. Okay, so we go out there in 2017, we get the survey. We have all kinds of problems apart from the frost everywhere that didn't go away till 3 in the afternoon. And we managed finally to get 1 line done. Now, our accommodation is actually just visible in this slide. It's almost on the survey, just at the top. At this time, we were staying in this house, and the equipment had stopped working or wasn't working very well, and we're having all these problems. And we were sitting around at dinner that night with a glass of wine over dinner, sort of drowning our sorrows. And Alan Ertel, God bless him, should I say that, was sitting in the other corner in the dark working on the data. And he said, hey guys, have a look at this. Look at this profile. The yellow and green lines are a profile of the data. In this case, there are 2 mixability values because we weren't combining the sum and difference frequencies at that stage. So what we would call mixability now would be an average of those 2 lines. And he said, look at this. There's a bump in the curve. Where does it lie? And we plot it, and it sits right where that green star is, right over our sulphides. And we went, yeah, so the drowning of our sorrows turned into toasts, and I think we probably opened another bottle on the strength of it. The next day, we looked at the results and we said, my goodness, but hang on a second. Look at this. Look out on the western end of the line. We've got super strong values out there. This thing is supposed to tell the difference between the black shale and the sulphides, but we're getting a strong signal. Why? How is that different from IP? Well, theoretically, it should be different. So we looked at it carefully and we noted that the wires, say the blue wire for one electrode and the red wire, were both either directly adjacent or whatever to the receiver where that question mark is there. And we thought, well, maybe there's something coming out of our transmitters. And we used our receiver to actually measure what was coming out of each of the two transmitters. And we found a major problem. The transmitters were interfering with each other. Although they were separated, there was a small amount of signal coming out of each of the transmitters and getting into the other transmitters. We were trying to develop a system that would find semiconductors, and we found them. What's an IP transmitter full of? Semiconductors. And so the signal from one is getting into the other. Our transmitters were actually producing the signal that we were looking for. Much scratching of head and whatever later. And so we thought, righto, there's a couple of ways of solving this problem. And the way we chose was to something called a rotary converter. We will get rid of all the electronics in our transmitter. Well, how do you do that? A rotary converter. A rotary converter is something that is basically an electric motor driving an alternator. So you go from electric to mechanical back to electric. And what you see here is the motor, which we can control very closely in frequency and phase, mechanically driving an alternator through a transformer and into the ground. So in the final circuit, which is the purple line there, we just have an alternator, a transformer, and the ground. There are no electronics in our final circuit. There are a large number of problems doing this, but the fact that there were no mixing signals in that first spectrum that I put up, I meant to illustrate that there were no mixing signals, illustrates that it actually does work. So we started building. Where we go, Andrew's budget starts disappearing very smartly. Here we are, where we go, where we go, where we go, it's building it up. It's taken a couple of years. Okay, until we finally have two systems for the two different frequencies that sit nicely on the back of a tray back Toyota. So 3 or 4 years later, we've had, this wasn't an easy process. 3 or 4 years later, after explosions, blown regulators, yeah, you name it, we had all sorts of fun. It was great. It's been heaps and heaps of fun. And we managed to explode a capacitor right on Alan Erdel's desk, which was probably the highlight of the whole process. And we've had several field trips as we went. We had the first field trip and it was freezing cold with the frost, and we had interference between the transmitter and the receiver. On the second field trip, it was the sleet, and I think the receiver misbehaved, so we got no coherent results out of that. On the third field trip, we decided we'd do it in summer. It was 42 degrees, a total fire ban, and one of our transformers caught fire. The fourth field trip, we decided we wouldn't work on coordinates, we could work on an air photo, and we put the electrodes in the wrong dams. And then in March this year, ladies and gentlemen, this is Mumbo number 5, our 5th trip, March this year. Now we've done everything right. We've got the wires going around the edge so they don't interfere with anything we're doing. They probably won't in a production sense anyway, but we're trying to eliminate all problems. So here's our survey lined up. And as an additional benefit, Fender happened to have a crew nearby in Blaney, just 20 minutes drive away. And they were able to take that crew from the survey they were on just for a couple of days and bring them over to help us out. Now, from the look of Andrew's face at the time, it was pretty clear that his client wasn't very happy about having his crew disappear. It was only for 2 or 3 days, but it's still. And so if out there in Zoomland, Anybody from that company is still there. Thank you. Thank you. It was probably a pain in the neck for you, but for us, it was a lifesaver. And one of the reasons was we had an IP crew with an IP system that we could connect to exactly the same wires and exactly the same system. We would have to do a direct comparison between what we were doing and what they were doing. So here we have it on the top of the hill at Kempfield. On the left is the Heterodyne transmitters sitting in the back of the truck. On the right, we have the IP truck transmitting into the same transmitters. It looks by this photo that the transmitter is actually running IP at the time. The operator's there and there's nobody at the Heterodyne system. Meanwhile, down in the system, Keith is down there with his receiver. Obviously on this slide, he's taking the readings because the IP crew is standing around waiting for their time. So let's talk about the results, which is what everybody came here for. So this is the IP results. This is IP chargeability from a gradient array survey. And over our sulfur deposit, we have a moderate anomaly, 20 millivolts above a sort of a 10 millivolt background. In the scheme of things on this property, that's not uncommon, not something that would attract your attention. It's an anomaly, but it's not unusual. Out on the western side, we have the Ordovician rocks, and particularly this rock that's hatched in here, which is actually mapped as chert, I think, but you'd have to suspect that it's graphitic shale. It's a weathering effect and it's graphitic shale underneath because it's strongly IP responsive, 40 millivolts per volt. We found another anomaly up here, which actually is away from any drilling, but there are drill holes further to the north. I don't know anything about the exploration program, so I can't comment on what that might be or not. I don't know. But we got pretty much what we expect as far as the black shale and the sulphide horizons are concerned. We got a moderate anomaly on the sulphides and a strong anomaly on the black shales. That's what you'd expect. Now just draw a couple of lines around those so you know where they are, and we'll have a look at what everybody's waiting for is the Heterodyne mixability results. What? There's a hole in the middle. Turns out that we were very careful about connecting the arrays of wires going outside, but nobody thought to connect the electrode that was directly under the receiver. And if you guys are sitting here thinking, what the hell, I've spent the last half hour listening to this ratbag up the front here, talking all this rubbish, waiting with bated breath for the results, and this comes up, there's a hole in the middle. I just want you to think about how we felt. When we got back to Sydney, I went, what? Our target, where is it? Anyway, so we thought we'd better have a look at the results anyway. We have an anomaly, a response to the south, down on the edge. That on the photo, on the satellite photo behind there, that's a pine forest. There's a rabbit-proof fence around it. So that line of readings runs right along the fence. So that's not surprising. Out on either side, we've got a high value that's perilously close to the transmitter electrode. In a normal survey, you wouldn't be anywhere near that close, even more close because of the mistake we made with the location. So we were really, really close to the electrode. So again, it's not surprising that we have a response on either side. Over our sulphide zone, we have rising values on either side, just not enough to say, yes, it's definitely there. But when you put it together with the fact that on our first survey, we got a bump exactly there, it's pretty likely that the sulphides respond. Up here, we got no idea. And I'll just overlay the IP. So in the center here, here's our IP anomaly, our known sulphide zone. It appears that we have an anomaly. We don't know for sure, but it's possible. Up here, this other IP anomaly, which we don't, that doesn't have any drill holes.
Geologist point of view, can you just run a finger shadow on that screen?
That's what it is. That line there. Can you see? Yeah, my cursor doesn't work.
No, but you can go up to the screen and make.
Oh God, it's technology again. I don't know anything about technology. Oh, manually. Okay, okay. These are the IP anomalies. Okay, here's our IP anomaly. We drew that line on the thing. Here, possibly a mixability anomaly, and the sulphides down the middle. Over here, we don't know. This spelled here, Ordovician, and spurious things due to cultural effects. Well, we're getting to that, Neil. Just be patient.
Okay.
I'll go back here. Hang on a second. Let's go back to the IP, okay? So the strongest IP anomaly is out on the western side, and I've drawn a line around. Do you see that, Neil? Good, okay, okay. We assume that is the black shale. It's in the Ordovician sediments, and so we assume that's black shale. So we go back to here, the same lines, they're on this slide too. You see them? Okay. I'm just going to talk about this first, okay? Up to the north in the center, we have the IP anomaly we had, which hasn't actually got any drill holes. And lo and behold, it does correspond to a mixability anomaly as well. And we have this other one further out here, which may be in Ordovician sediments, but the geology is out there is actually ambiguous. It shows interbedded, or not interbedded, interfingering Ordovician and Silurian rock. So we don't know. We've got no idea what that is. The critical thing of all this, you can ignore all the rest of that stuff, because the critical thing is that we are pretty sure that our sulphide zone has a mixability anomaly on it. Not guaranteed. We have to repeat it. And we are very sure that the graphitic zone, which came up in the IP, does not. That is the Holy Grail. That's what we were after. Okay, so that's where we were up to. I'd like to give you more, but we haven't got there yet. We'd like to be able to give it to you, but it's not happened. So where do we go from here? Well, for a starter, we've got to repeat the survey. We're going out probably in September. We'll give the results of that. Yeah, after depending on Andrew, and after the weather warms up a little bit. We hope to release that data at the AGC conference in Brisbane in March. And that will either be, we stuffed up and it doesn't repeat. We've got no idea what's going on. It'll be, oh yeah, okay, this is great. There we go. We've got to ruggedize the equipment. At the moment, it's a bit of a rat's nest, and part of that problem is the reason we missed the electrode and stuffed that up. We'd like to encourage, we can't keep out and go, we can't keep on going out doing this by ourselves. So we figure it's at a stage where we can encourage companies to give it a try, even with a caveat that we really don't know what the hell it means. We actually have several companies already come to us saying they don't care. We're interested in giving this a try. We'd like to look at the higher order effects, the higher order mixing terms, and we've already started to do that, but in the process have discovered some problems with the frequencies we're using. And one advantage of having to go back out in the field again is that we'll use the right frequencies next time. Years ago, we started off worrying about a DC bias, which is the idea of putting a DC current across, like an IP transmitter, across the whole thing to shift the position on the curve. You've got a curve that's not linear, it's bent. Well, if you put a DC bias, you can put your operating thing onto a different part of the curve, do you get different results? If you do, that's telling you something about what's under the ground. Now, this is the fantasizing stuff. What's going to happen? And I figure if you're going to fantasize, you know, why would you dream about making $1 million when you can dream about making $1 billion? It's just a dream. So this is in the same category. It has the potential to be able to distinguish one mineral from another. Unlike, say, resistivity EM or whatever, it doesn't depend on the conductivity. It depends on things like the semiconducting properties of sort of quantum physics, almost values about how much doping, how much impurity there is in each of those minerals. So if you happen to have a particular impurity in your ore body, it will affect the semiconducting properties. We don't know, chances are small, but it's nice to fantasize about. Routine incorporation into IP surveys, I think that's a given, and probably when we start doing a few more surveys, we will just do that routinely. It's just going to happen. The third one, and I'd like to thank Jim McNay, who's in the audience here somewhere, who flew up specially from Melbourne to have a look, is investigating airborne IP systems. We think it's possibly amenable to airborne systems. One of our field trips and a lot of the laboratory work we did were using much higher frequencies, 10 times, like 400 to 600 hertz. That's the range that you can use an airborne electromagnetic system, and there seems to be no difference. That makes sense because unlike IP, IP is an electrochemical effect, and that happens slowly. This is an electronic effect. Electronics works to gigahertz. So it should be no difference, and that's actually what we've found so far in our laboratory tests. So there is a real chance of developing an airborne system, but that's me fantasizing again. Detection of poorly conducting minerals is what I was just talking about. Broken Hill, Mississippi Valley. I mean, who knows? It's not the conductivity that counts. Who knows whether impure sphalerite touching galena in a Mississippi Valley wouldn't produce this effect and be mappable where there's nothing else that works. No geophysical techniques and very few geochemical techniques that work with that style of deposit. And the fame and fortune, well, it's nice to think about, but unfortunately, we're really probably too old to be bothered. So we started off wanting to pull a rabbit out of a hat. And it hasn't quite worked out like we thought. There's been a few surprises. And we're not quite there yet. But we're really close. We are really, really close. This has been really quite exciting. And hopefully by September, we'll get really definitive results that will say one way or other, yes, it works, or no, it doesn't. And that would be really great. So stay tuned, AGC in March. Hang on. I want to say some thanks because it's really important. Fender came in and it was going to cost some money. And there was probably nothing in it for them, possibly, other than possibly entertaining. Yeah, they're one of the few geophysical contracting companies that employs geophysicists. And I think Andrew thought this would be a good thing because we can keep our operators amused and maybe keep them hang on for a while before they get totally bored by the mundane fieldwork. And Fender have been astounding, really, really fantastic partners. Taronga Resources, that's Bob's company. Arctan Services used to be my company. CSIRO have been fantastic with the laboratory work and providing Keith, who's been absolutely invaluable. And of course, Argent Minerals, who provide the field test site for us, has been great. And there've been a few other people, Rob Blackwell's helped with computing and various other people. But there's one guy who I really want to mention. In 1970, there was a very strange fellow, a physicist at Macquarie University. He was so strange, he had been ostracized by the National Standards Laboratory, which is where he worked. He couldn't get on with anybody, and they'd parked him at Macquarie University. He thought of this. It's his idea. Bill Core thought of this. Now, Bill would be 100 now, at least, I think. So my guess is he's up there in heaven giving them hell. And he might be a mate of Dave Timms. So I'd really like to thank Bill and acknowledge him because it's his idea. And thank all the other people that were involved. It's been fantastic. It's been a hoot. We loved it. Thank you.
Okay, we've got 10 questions online. We'll run through those first, I think, because really for dinner, we want to be downstairs by about 7:30. Now, who's involved in the ASEG who knows how to run the online questions? No? Can you run that for me, please? Get Barbie to do that. Yeah. Then we'll take some questions from the floor and any more questions downstairs. You have to go.
Yeah.
So magic fingers. Who knows?
All right. So we have one from Mike Smith. So Mike in the Southern Morano tonight. Really stimulating talk. Thanks, Steve. Listeners may not know that ASEG History Committee has recognized Bob White's early work on the conformation of non-linear electrical effects in mineralized rocks.
Yeah, that's good. I'm actually on that committee, so.
Yeah. Okay. And actually, I think all of these are from Mike Smith. So continuing from above, recognize Bob White's early work on, yeah, all right, as a significant, yeah, okay.
I think he corrects it below.
So here's a question by Stevens. Who first?
Significant milestone.
Identified.
Oh, it's milestone, yeah.
Okay, it's historic. The mines have been there from hundreds of years, and I don't know. That's out of my. That you have to ask Argent and various people. It's not. Vlad might know. I don't know. Where's Vlad? I don't know. It was a long. It's historic, and it's got nothing to do with what we're doing. Basically, it's got nothing to do with the talk.
Okay, so there's a question from an anonymous attendee. So, can the same technology be applied on pole dipole or pole dipole survey configuration?
Yeah, interesting question. We've looked at obviously where you go. Okay, we started with gradient array or a gradient array like array. There are. The obvious thing is, where do you go now? What other types of surveys do you use? It's not straightforward because the results probably depend on the current density. So if you've got a moving transmitter, you may get all sorts of, we don't know. One interesting thing that comes out of this is this question of DC bias. And one of the possibilities that we look at, we hope to look at in the future, is putting out a gradient array type array for the heterodyne signal and then doing a dipole-dipole IP survey in the middle of it. That way, the signal from the IP would act as a bias. You've got positive, zero, negative. You've got three signals, three different biases. What effect does that have? That's a possibility for the long future. At the moment, we don't even know if it works, so we're doing it as simply as we can.
Right, so keep going. So there's a question on the resolution, size, and depth.
I've already answered that one. We don't have a clue. We don't even know if it works yet.
Yeah, a few comments. One from David Platt. Very interesting presentation. Keep up the good work and have a few cases of ASEG work.
I already have.
Yeah. Yeah. Few more comments. Great talk from Mark Lackey, from one from our illustrious president Stephanie Kovac. Interesting talk. Thanks, Steve. Question from Julian Wadzicki. So one possibility within the airborne configuration could be to use 2 heavy-duty UAVs in tandem at either end of the transmitting electrodes.
Not possible. I was talking to Jim McNay about airborne IP earlier on. The most logical way to do the airborne thing is to have it like a standard airborne transmitter. One of the advantages of that is because the loop that you use in a transmitter in the air is perfectly linear, you don't have to worry about separating the 2 frequencies. You can actually transmit them into the same loop. The problem with airborne will be, do you get enough current density in the ground to cause the effect? Unknown. I would love somebody to try it, and I'm pressuring Jim to go out there and give it a go.
Cool. So a few more. If every technique known to man and some not tried at Kempfield, and with barite lenses being massively dense, why doesn't high-res gravity show up at least the barite lenses plus massive sulfide lenses?
That's an exploration question, not a research question. I did work on this project more than a decade ago. There is good gravity data, good high resolution gravity data. I don't remember the results, and it's not particularly relevant to the talk.
And a question from Justin Ward asking, are there any plans to create synthetic Ford models? This would help optimize survey planning and resolution.
I'm not sure what you mean by synthetic models. Do you mean physical models or computer models? We have no idea what do a billion somewhat diodes buried in an unknown mesh, what effect does that have? We've got some ideas, but we don't know. So making a model is not really feasible at this stage. One of the things we've considered in interpretation is just to assume that our signal, not worry about the transmitter, just assume that our signal is generated in the ground and is radiating out. And it might be possible just to put the results into an IP modeling system and model it that way. And we'll certainly try that when we get some decent data.
Looks like we've got 2 more on there. We'll take these 2 more comments with the end ones. Oh, okay. Okay, thanks for reminding. Take a couple of questions from the floor here. Okay. Flat first, then Arnie.
Steve, that was great, though. And second, did you try to put a survey for results?
Yeah, I've stayed away. The question was, for those out there if they didn't hear that, how do you compare it with the SAM results? Yes, I have looked at that. I don't remember exactly. Nothing stood out as being similar, and really, it's again, it's a sort of an exploration program, an exploration question. It's about the exploration of the prospect. As far as our project is concerned, we know nothing about it. As it turns out, of course, I do because I work there. But it's not particularly relevant to what we're looking for. SAM will respond to the resistivity structure of the ground. We're normalizing that out. So you wouldn't necessarily expect any. It's a different property. It's entirely different. That's hard to get through to people. Say, what about IP that's been done? No, it's actually an entirely different physical property.
Steve,
I found tonight very interesting. Being a former amateur radio operator, back in the 50s and 60s, when I was building my own equipment, a BFO was used to beat CW code to get a signal to noise ratio, high signal to noise ratio, more particularly with single sideband. And BFO's been around a long time, and that's what intrigued me about.
Okay, that's really, it's really interesting. It's really hard to work on this project without getting deeply involved in electronics, electrical engineering, signal processing and a whole bunch of other things. You may not have noticed, but there were actually sidebands on some of those primary signals, which we think is due to modulation. It's the controller of the speed of the transmitter just shuffling backwards and forwards as it tries to keep the phase and the frequency right, and that produces additional spikes, which are the sidebands on either side of the transmitter. But it's not particularly relevant to the development of the program.
Okay, so before I get Barbie to the vote of thanks to Steve, just a reminder, thank you all for coming. Dinner downstairs, I've said 7:30. And next month's talk is the 50th anniversary conference and dinner. Our keynote speaker is going to be Dick Silito, so it's going to be a fantastic conference. And the bookings will close on the 17th of August. So I'll pass on to Barbie now.
So yeah, on behalf of ASEG and also SMED, thank you very much for your presentation. It was really fantastic. And
Thanks, Bobby.
Can we get a photo in front of? We'll get a photo for
yeah, sure.
magazine.
Okay.
Yeah. All right.